All right, next I'd like to look at some of the properties of black holes. And so these are all based on Einstein's general theory of relativity, which I'm going to need to go over with you in a little while. But let's just look at why we need general relativity. It turns out that there are some very bizarre properties that black holes have. And in order to explain them, we're going to need a new theory of gravitation. So just in summary, we have the event horizon. This is basically the point of no return. Because once we cross the event horizon, nothing can escape, not even light. So this is the point then that we mentioned before, where the escape velocity becomes greater than the speed of light. And so nothing can escape because nothing can move faster than the speed of light. And in the center we have the singularity. So this is where all the mass of the black hole is concentrated. And it's a point essentially of very small size and almost infinite density. So if we look at the end states for a star, like for example a neutron star, this is held up by neutron forces. It's about 5 miles across. And it's supported then by the repulsion of the neutrons. And stops it from collapsing that last little bit that would turn it into a black hole. For a white dwarf, it's a bigger object, about the size of the Earth. And supported by electron forces, because the electrons tend to float to the surface of the star, and then they want to stay away from each other because of their repulsion, and because of quantum mechanical interactions. And so the white dwarf then is supported by electron forces at about the size of the Earth. That a black hole is at a point where no known force in the universe can stop the collapse. So if you get to a mass that's greater than about 3 times the mass of our sun, then no known force in the universe can stop this collapse. And all of the mass essentially smashes down to what we could consider to be essentially, well, smaller than the head of a pin at least, and maybe pretty close to 0 size, or at least a point at which size has no meaning anymore. Sometimes that distance is referred to as the Planck length, which is as much smaller than a bacterium is, as a bacterium is smaller than the galaxy. And so the Planck length is an exceptionally small distance. And so that might be the point at which the mass is concentrated. But anyway, it's highly compressed. And then the size of the black hole is defined by the event horizon. Okay, so the size of the event horizon is about 3 kilometers for every mass. That's about 2 miles for every solar mass in the singularity. So this means that we can have the zone of darkness that surrounds the black hole being huge if we had a big enough singularity, a big enough concentration of mass at the center. And we want to call it, I guess, a big singularity, which is a high mass singularity, because it's not big in size, and yet it could be very, very high in mass. So there have been huge black holes discovered that have something like 40 billion times the mass of our sun. And they have zones of darkness that might extend out to about the size of our solar system, okay, all the way out to the outer planets. And so there are some black holes that are quite a bit bigger that are associated with black holes that you would see at the centers of most galaxies. And we'll get to those later. But for the moment, we're just talking about stellar-sized black holes, ones that may have a size on the order of maybe a few miles in terms of the radius of the event horizon. And so let's say that you were a spacecraft and your mission was to study the black hole, okay? And so you come in, let's say, to the black hole, and you go into orbit around it. But you're very careful not to cross over the event horizon. Why? Because Einstein tells us nothing can escape from beyond the event horizon of a black hole. Right? And so you go, okay, I won't do that. And so you go, but I want to see what's inside, so how can I do it? I know. I'll lower a camera down into the black hole beyond the event horizon, and I'll take some pictures. And then if something happens to the camera, no big deal. You know, just chalk it up to a failed experiment. And so you start trying to lower this thing, and a couple of weeks later, the captain goes, hey, can you speed that up a little bit? I don't see any progress being made. And the engineer goes, well, I'm sorry, Captain, but it appears as though it's going to take an infinite amount of time for the camera to cross the event horizon. And so the captain, not very satisfied with that explanation. And so he goes, okay, what the heck? We've got the most powerful ship in the fleet. We'll just dip in, take a quick little look. Now, what do you suppose you might find if you went beyond the event horizon of a black hole? Well, nobody knows. It is something that we can't observe, and it may take on a completely different set of rules from what we normally think of as being real. Some people have speculated that you might see yourself moving backward in time, but we don't know. It's just speculation. That Captain wants to know, so foolishly, he drops down below the event horizon of the black hole. He starts looking around. He goes, wow, this is really cool. Let's start snapping off some pictures. I don't know what he saw, but he goes, wait till my friends back at NASA Control hear about this. And so he goes, okay, engineer, let's get out of here. And so he fires his engines. He's got everything, matter, antimatter, converters, you know. This thing has the power of a galaxy. But it's not doing any good. The ship continues to spiral inward toward the singularity. So he starts getting worried. He goes, uh-oh, I'd better radio to the outside universe for help. And, but guess what? Nothing can escape from the event horizon of a black hole. Not even light or radio waves or anything else. They all travel at the speed of light. And so this isn't going to do any good either. So eventually, as we mentioned last time, the force on the head of the person becomes larger than, less than the force on the feet, and so you get these tidal forces that just stretch you out into a long piece of spaghetti and then snap you in half. Then those halves would be snapped in half, and then those halves would be snapped in half again. That process of bifurcation would continue perhaps hundreds of times, and then all of that, those little pieces of mass would be crushed to zero size by the singularity of the black hole. So that's it. That's the end of the finest starship in the fleet. But there was a sister ship that pulls into orbit, and her job is to find out what happened to the other ship. And so she goes, don't worry, I'm not going to cross the event horizon, but I'm going to try to get an idea of what's going on. And so she pulls into a very tight orbit around the event horizon. And then she pulls in a little closer, then a little closer, a little closer, a little closer, and then she starts to radio back to the Earth, and what she finds in her closed circuit communications with the Earth is that the people are running around like crazy. They're just moving really, really fast. And they're talking so fast that she doesn't even understand what they say. And they're looking at her, though, and they're seeing her time as being very slowed down like this. And so they wonder whether there's something wrong with her, some kind of space sickness or something. But no, they see that the clock itself is ticking off more slowly. And so they realize that there's nothing wrong with the captain. It's just that time is going more slowly near the event horizon. And so this is predicted by Einstein's theory, and this is one of the reasons why I'm going to have to go back and explain Einstein's theory of general relativity so that we can at least get some kind of an idea of why this is happening. Okay, and so she goes, okay, well, I can't even understand what you're saying. You're talking so fast, but I'm pulling in a little tighter. And they're going, no, 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 but you can't hear what they're saying. And, but then from their point of view, they see hers going more slowly. And so she sees the Earth going faster. That the Earth sees hers going slower. Near the event horizon. So she pulls in a little tighter, and then all of a sudden, everything just kind of blurs out on her picture from NASA control. She goes, okay, well, I better pan out to a longer distance view of the Earth-Sun system. And so what she sees is the Earth going around the Sun like this. So that one of her seconds is like 100 or even 1,000 Earth years. But from the Earth's point of view, she's hardly moving at all. So she's going so slowly that it might take 100 years just for 1/10 of a second to go off on her clock. And so, but she realizes, even though from her own point of view, her own time is going normal, she realizes that something terrible has gone wrong. So she pulls away from the orbit of the black hole and hustles home at breakneck speeds, and then lands on the Earth, make sure that everything's okay, but guess what? It's 10 million AD. So she's gone 10, although she's and her crew have only aged a couple of years. The Earth has gone through 10 million years of time. And in that amount of time, not only is NASA control gone, but humans have gone extinct and the rats have taken over. And so she's captured, she and her crew are captured and interrogated by the rats. Okay? And so that's the kind of thing that can happen then when you mess around with black holes. Okay, so let's try to understand though why these kinds of things happen. And so in order to do that, we need to go back to Einstein's theory of general relativity. Don't feel threatened by this. It's just a few rules that we can use to help us understand these principles. Now we're not going to do any nasty mathematics here. This is just going to be a conceptual kind of a thing. So in Einstein's general theory of relativity, there are basically two statements that we can make that explain his theory of gravitation. Okay, so this is a new theory of gravity. It's called the new physics, although he did this in 1905. It's new in relationship to Isaac Newton. But we define space to be four-dimensional, to not only have the dimensions of regular space, length, width, and depth, but also of time. And so his statement basically then is space tells matter how to move, matter tells space how to curve. And so if we understand this, these two statements, we can understand Einstein's theory, at least at a conceptual level. So by space here, we mean space-time. So we're talking about taking the dimensions of space and incorporating them in with the time dimension into a four-dimensional surface. I can't show you what a four-dimensional surface looks like, but I can show you three-dimensional surfaces in which we've suppressed one of the dimensions so that we can get an idea of how this could work. Okay, and so mathematically then you can do this, but not even Einstein could visualize four-dimensional space. So anytime that we see space here, what we're really talking about is a four-dimensional space-time. So you could imagine then a shape that has all positions and all times in it. So this might be us here. This might be Andromeda Galaxy a billion years from now. And this might be you at the place and time of your birth. And so here you've taken this tortuous path from the place and time of your birth to where we are here. But then every point on this four-dimensionally curved surface would be a point in space and time of our universe. And so it would contain all past events, all future events, everything that's in space and everything that's in time too, as a four-dimensional shape. And so this is kind of a bizarre concept. And so we might wonder, well, why use this? And the answer is because it helps us understand some of these weird things that are happening with black holes and with other exotic objects in the universe. And so the test of it is whether or not it gives you the right answer. And Einstein was able to show that using this concept of the four-dimensional space-time, we could explain gravity in a way that Isaac Newton couldn't explain with his inverse square law. So matter tells space how to curve. What does that mean? Well, it means that the presence of matter bends space and time, because space is called 4D space-time here. And so you could imagine then, if we just look up at the data projector for a second, that you're near a black hole. So the presence of matter near a black hole could bend the space so much that the light couldn't escape. it would basically be traveling along closed loop paths because the curvature of the space could bend it right back around on itself. And so that's the idea that you could get such an enormous warping of space and time that the paths that objects would take in trying to escape from a black hole would just bring them right back around to their starting point because the space and time itself would be curved back around on itself. And so that's what happens then when you go beyond the event horizon of a black hole. It's that you have this highly curved space, so curved that you can't get away. And this is the reason why the spaceship couldn't escape. Once it got inside the event horizon, then space tells matter how to move. And so when the rocket ship was inside of the event horizon, trying to get out, the space itself that it was traveling along was in a closed loop. And so if you're traveling inside of the event horizon and you're still alive, you haven't been stretched apart by tidal forces, you could see the back of your head because you would see this curved piece of space curving back around so that you would see the backside of your body because the space and the light that's traveling through that space would be curved back around on itself. And so the light that was coming from the backside of your body would come around and you would see it from the front. Okay? And that is one of the weird things about general relativity. Now, to try to understand this better, let's imagine that we're on a flat, horizontal surface, like the surface of a trampoline membrane. Okay? And then let's roll a marble along that surface. Okay? So that marble is going to be quite happy to travel in a straight line at constant speed. But now let's say that you put a big bowling ball in the middle of it. Okay, that bowling ball is going to bend the space, and so now the marble might travel a curved path around that bowling ball. Not because the bowling ball is having a direct influence on the marble, but because the bowling ball curved the space that the mass was moving through. And so this is like having a marble that you roll around inside of a bowl. So you take inside of a bowl, you take a marble and throw it sideways, you can get it going around in a curved path. And so it's really just traveling in a straight line path through the path of minimum distance through a curved surface. And so that's what gravity is, according to Einstein, is just this tendency for objects to travel through curvatures in space and time that we can't spatially see. And so we call that gravity, but it's just an illusion, according to Einstein. Here's another way of looking at it. Let's imagine that you're a two-dimensional creature, a flatlander, that on the surface of a three-dimensional sphere. But you can't see the three dimensions of the sphere. You just see, because you're two-dimensional, the surface. It's a curved surface, but you don't know it's curved because you can't see in that third dimension. So you take off in a race with another ship from the equator, and your destination is the North Pole. What you'll notice then is that some mysterious force seems to be drawing you together. And so you can imagine this direction be the direction of time, and this to be the direction of space. Okay, so I'm suppressing several spatial dimensions here, but let's say you're moving through space in one dimension, and then let's make this time, sorry. Let's make this space. So we'll measure space as the distance between the rockets, and time as being the path that it takes on this three-dimensional surface. So what you notice then is that the space between you and that ship, even though you're taking off in parallel directions, is getting less. And so then you could set up some inverse square law of gravity that would explain that, and would explain the attraction between these two objects. It's not really happening at all. What's happening is that you and this other object are just moving along through curvatures in space that naturally tend to bring you together because of the curvature of the space you're moving through. But you can't see all those different curves because we're in a lower dimensional awareness of what's going on. Okay, so this idea then is Einstein's idea of curved space and time. The matter puts curves in the space, but then the space gives the matter moving instructions. Okay, so the matter gets moving instructions from the curved space that it moves through. You get into highly complex mathematics when you try to explain this the way that Einstein did when he discovered general relativity. But we can still talk about it from a conceptual point of view. And so what does this do for us that Newton's inverse square law of gravity didn't do for us? Well, let's take a look again at the data projector. Here's some evidence for general relativity being right. Einstein realized that the curvature of space of the sun should bend light that comes from a distant star. But you can only see the light from a star during a total eclipse. And so Einstein then started lobbying scientists to go and see if they could find the shift in the position of a star in which the path that the light takes from the star brings it close to the surface of the sun. And by doing this, he was able to predict the exact right amount of shift that was consistent with his general theory. So this is something that Newton's law of gravity didn't predict, because Newton said that gravity doesn't bend light. But Einstein's theory said that it did. And so there are many, many other experiments like this that have been used to prove that Einstein's theory of gravitation is a better way of looking at gravity than Newton's inverse square law, and works particularly well for exotic objects like black holes. So near the event horizon, time stretches to infinity. And space contracts. By contractor, I mean it bends back on itself. So this, again, is the reason why you couldn't escape, why the rocket was confined, even with the most powerful rocket that you could ever imagine. That rocket has to keep following this closed loop path because the space is curved back around on itself inside of the event horizon. So that's what happens with the spatial dimensions. But the time dimension stretches to infinity. And so let's say that we're back in that situation where the astronaut was near the black hole. And so then we could talk about 1 second near the event horizon as being highly stretched out, if you could imagine time to have a length. And then 1 second on the Earth. Not stretched out because it's far away from the curvature of the black hole. So then one thing that we could say that both observers could agree upon is that there'd be many, many Earth seconds for 1 second near the event horizon. That what you see if you're in the rocket near the event horizon is your own time going normally. So what you see then is a whole bunch of Earth seconds for every 1 second that you see. Or in other words, what you see is the Earth sped up. And the Earth going around the sun super fast if the increments in time become greatly different from each other. But on the other hand, 1 second on the Earth looking at what's happening to the astronaut near the event horizon is going to see only the tiniest fraction of a second go by. And so that means that she's essentially going to look like she's frozen in time. And it might take 1,000 years for you to see 1 second go off on her clock. Okay, and so this is the result. I'm not explaining why this is true. I'm just saying that when you solve Einstein's field equations, the time dimension, if you can imagine time to be like a rubber band, gets really stretched out. The spatial dimensions get really collapsed. And this is the reason for the differences in what we see when we look from, say, the Earth's point of view or the rocket's point of view. And so another thing that this tells us then is that because time stretches to infinity at the event horizon, is that if you were going to cross the event horizon, from your own point of view, it would only take a few moments. So the rocket's point of view then, it just sees this happening in a couple of seconds. But from the Earth's point of view, the rocket never makes it to the event horizon. Because it takes an infinite amount of Earth time for the rocket to cross the event horizon. So infinite time must pass before the Earth would see the rocket cross the event horizon. So if it never sees it cross the event horizon, what does the Earth see? Well, the Earth sees the rocket approach the event horizon at an ever-decreasing rate. In other words, be at this point, come in pretty fast, then slower, 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 and that last little bit would take infinitely long. That's like that Woody Allen quote. Infinity's a really long time, especially near the end. And so that's what the Earth would see then, is it'd see the rocket never reaching the event horizon in a finite amount of time. And yet there's a strange consistency between the two, because here we see that the rocket crosses the event horizon, but infinite time passes in the external universe. From the rocket's point of view. As the rocket crosses the event horizon, you'd see a bright flash of light. That would be basically all of the stars in the universe burning out all of their energy over an infinite amount of time. And so we see completely different things then from these different points of view, and that's why they call it relativity, because it's relative to your point of view. You have different realities based on which point of view you're in. Okay, and the Earth would see the rocket approaching the event horizon at an ever-decreasing rate, but eventually it would seem to disappear. The reason for that is that 1 second here would be like 10,000 Earth years, and so that means that 1 second's worth of light would be stretched out over 10,000 years of Earth time. And so the number of photons that you receive would become unmeasurably small, and it would appear as though the rocket had disappeared beyond the event horizon. And there'd be no way of telling whether it did or not, because there's no experiment that you could perform, because the photons of light would be so stretched out over time that the thing would just disappear from view, and no matter how accurate your measuring instrument was, it wouldn't have the resolution that was necessary to still see the rocket above the event horizon. But nevertheless, this is what we would expect from these different points of view, because of the fact that time stretches to close to infinity near the event horizon.